Comets, like asteroids, also contain clues to our origins. Discovery's comet missions are beginning to shed light on the conditions present during the earliest time of solar system formation. Stardust, NASA's first mission dedicated to exploring a comet, ventured deep into space to collect and return extraterrestrial material to Earth to answer key questions about the formation of the solar system. Stardust collected particles of interstellar dust before carrying out its main task, capturing cometary dust during a close encounter with comet Wild 2. Don Brownlee is the Stardust principal investigator.
We were flying as close as we dared to the comet. We wanted to collect dust, so the closer we get, the more dust that we find. When they're in the inner solar system, near where Earth is, they're actually physically coming apart. The heating from the sun vaporized ices. The ices leave us gas, and they release dust and rocks that were glued together by the ices. The spacecraft was designed to withstand the impact of a rock about the size of a grate. I mean, these rocks are coming at you at 6 kilometers per second. So it was a very violent collision with a rock.
Despite flying through the treacherous coma cloud of Wild 2, Stardust performed flawlessly. A clever trajectory maneuvered the spacecraft to within 150 miles of the nucleus. An extraordinary substance housed in the tennis racket-sized collector grid called aerogel captured thousands of tiny cosmic particles without altering their shape or chemical composition. Aerogel is a silica-based solid that is 99.8% air and 1,000 times less dense than glass, the lightest known solid as listed in the Guinness Book of World Records. After the comet flyby, scientists were stunned by the pictures and the data sent back from the instruments on board.
And the first picture we got down was just a stunning, stunning image. This was a body with huge features on it. I mean, it's 4.5 kilometers in diameter, but there were features on it. There were 1.5 kilometers across, and these were big pockets in the surface. The primary ones we saw first we call left foot and right foot because they look just like someone in clown shoes stepped in this surface and left imprints of the left and right foot.
Unexpected images were captured as jets of gas and dust that create the tail were ejected from the comet.
We expected to see one jet from the comet, and we saw at least 22. Only a small fraction of the comet's surface is actually active, but these are the areas where the gas is coming out, and it's squirting jets of dust and rocks out into space.
The best was yet to come, when the samples returned to Earth 2 years after its close encounter with Wild 2. The return capsule descending from the sky looked itself like a cometary object.
And it's this fantastic golden-colored object, getting brighter and brighter and brighter. And it had this tail, luminescent tail behind it. You know, it was like from a Disney movie with a fairy godmother waving this magic wand across the sky with stardust falling off behind it.
The main parachute opened at 12,000 feet.
Okay, we have confirmation of a main chute here.
Okay.
All stations, main chute is open. We're coming down slowly.
The capsule descended in the dark and came to rest in the Utah desert, bringing back to Earth the first particles from a comet for intensive long-term study at the Johnson Space Center. Scientists discovered thousands of comet particles had been successfully captured at the end of long carrot-shaped trails in the aerogel cubes.
98% have these nice particles at the end, and most of them you could actually see with the naked eye. So this was a real thrill, and this was a very exciting time to work on this.
The most important thing is that these samples are back on the ground and that they'll be here for generations to come. People were out there worrying about, what's going to motivate children to go to school and stay in school or learn about science or math. This kind of data set does that. These samples really are a resource, not just for data, but also for education.
The Stardust mission has given the worldwide science community an opportunity to analyze the earliest materials that created the solar system, part of the continuing quest to discover the building blocks of life on Earth. Deep Impact carried out an incredibly complex experiment in space, probing beneath the surface of a comet to reveal the secrets of its interior. Traveling at 23,000 miles per hour, the larger flyby spacecraft released a smaller impactor spacecraft into the path of Comet Tempel 1. With spectacular results, audiences around the world witnessed the brilliant release of dust upon impact, as dramatic images from both spacecraft were revealed in near real time on NASA TV and over the internet. The Spitzer, Hubble, and Chandra space telescopes observed from space, while an unprecedented global network of professional and amateur astronomers captured views of the impact 83 million miles from Earth. The mission revealed several surprises about the nature of the nucleus of Tempel 1 and the origin of comets. On approach, several bright but short-lived outbursts were detected by the spacecraft and by ground-based observers. Deep Impact found evidence that the nucleus contains regions with different layering, suggesting the union of two or more separate pieces during comet formation. The comet is porous and fragile. You could pull it apart with your hands. Scientists were surprised to see impact craters, the first observed on a cometary nucleus. This implies a surface millions of years old, while nearby there are smooth, very young surfaces. As expected, scientists detected ice, since comets form in the solar system's cold outer regions, but they were surprised to find ice on the surface. They also found minerals from the hot inner regions of the solar system, and carbonates and sulfides that formed at more moderate temperatures. How did they get there? Scientists continue to examine the data. Together with the knowledge gained by other discovery missions, Deep Impact